Hi everyone, my name is Brandon and today I'm going to be going over my project for AgAid, which was building a soil crop residue estimator mobile application. First, a little bit about me. I'm an undergrad studying computer science at Washington State University, and this summer I had the pleasure of working with Dr. Kirti Rajagopalan. I'm always interested in learning new technologies and improving my development skills, so being able to explore machine learning and app development was really exciting for me. So what is crop residue, why is it important, and why is this app relevant? Crop residue refers to the organic material left behind after agricultural processes like harvests. It's important because it offers many benefits like reduced soil erosion, increased soil productivity, and it's also a good indicator of sustainable tillage practices. For this reason, it's important to monitor these crop residue levels. The motivation for this app stems specifically from the time and effort required by the current methods for estimating these levels. Take the line transect method, which is illustrated at the bottom of this slide. It involves manually counting the number of residue or non-residue occurrences along a straight edge, which you can imagine is a lot more work than just taking a picture of the ground. Finally, a significant user base stands to benefit from an improved residue estimator, and I'll go more into detail on that on the next slide. Since crop residue levels are so important for sustainability, the main groups that would benefit from this app would be conservation districts and the Natural Resources Conservation Services. These groups send out workers every year to thousands of tracts to take crop residue measurements, and I was able to meet with several representatives from these groups at a conference recently. They expressed great interest in this app, and it was helpful to validate this idea. So to summarize, the primary goal of this project was to develop a user-friendly mobile application that provides accurate estimates of soil crop residue levels. Here you can see the general workflow that was used to build this app. So the model and the mobile app can start separately in parallel, and basically the model will go under an iterative process of continual improvement until it reaches an accuracy that's satisfactory. At that point, it can be converted and directly integrated into the app, and the two pipelines merge into one. Let's first talk about the pipeline to build the machine learning model. And the first step for that is data collection. The images in our dataset were taken at 16 locations across Whitman County. And there's a lot more information on this slide about those images, but the important things to note are that they were taken from a smartphone camera at handheld height. So these images are very similar to what we would expect in our actual use case. So after data collection, we have to label our images. This is the first out of 2 rounds of labeling, where we're just labeling residue versus non-residue. And we're using a lab kit from Fiji, which has an in-house classifier. Basically, it makes labeling a lot more efficient because we can just provide a small number of samples. For example, the middle image, you can see we didn't label that much, but the in-house classifier is good at taking that and labeling the rest of the image for us. We just have to make sure that it's labeling things correctly. This was our second round of labeling, which was sunlit and shaded labels. The purpose of these labels was to help our model differentiate between, say, a lighter sunlit piece of dirt versus a darker shaded piece of residue. And so combining these 2 rounds of labeling gives us four total distinct labels. As for the model construction, we chose to use TensorFlow because of its conversion support to TensorFlow Lite, which is just an optimized version of the model that can run on smartphones. And we used pixel-wise classification because we have to manually label our dataset, which means that our dataset's probably too small for deep learning. And we use a MLP, a multi-layer perceptron classifier, because of previously observed success from a USDA advisor. And that model has 3 hidden layers and 1 input and 1 output layer. On the bottom, you can kind of get an idea of the pipeline we used to build the actual model. All right, so to train our model, first we needed to generate our features, which included types of features like color and texture. So for each pixel, we split it into 9 color channels, and then we applied 12 filters. 9 times 12 gives us 108 features per pixel. As for our data split, it was 80% training and 20% 80% testing, and within the training dataset, we split it again into 80% and 20% for validation. That gave us around 8 million samples, and we trained that for our initial model for 10 epochs. That initial model ended up with a bias towards predicting non-residue, and this was likely because of a training data imbalance where there was a lot more training samples that were non-residue versus residue. And we used importance weighting to try to counteract that, and we were rewarded with a slight accuracy increase. But more importantly, the bias was reduced, and that put us in a good place to introduce more training data to improve the overall accuracy of the model. We also used the TensorFlow Lite API that TensorFlow provided to test a light version of that model, and it resulted in the expected accuracy. It was around the same accuracy, and this is a good sign for the conversion process. All right, moving on to the mobile app side of the project. The first step was planning, and there were several important considerations that guided my technical decisions. Most importantly, the development time period was narrow, so tools for a fast development process were needed. Secondly, the users would probably be using the app in the field, so we would want to avoid reliance on connectivity or cloud tools. And related to the time consideration, cross-platform compatibility would be preferred because it would take much longer to build separate iOS and Android versions. So with these considerations in mind, I chose to use Flutter to build the app because of its fast development time and cross-platform compatibility. I chose TensorFlow Lite for the on-device capabilities. And finally, I used a prototyping process to speed up development and get quick feedback. For the prototyping process, these were the 4 features that I deemed as the minimum feature set. They're just taking a photo, getting the percentage of the crop residue from that photo, saving the residue readings in an organized manner, and finally being able to export the readings to an external drive or device. So in our current state, we have a prototype with the minimum feature set implemented, albeit without the actual crop residue model. This is because I'm currently working through the issue of on-device feature generation. Even though the Lite model runs fine locally, the image processing required for generating the features is a big challenge. So the app might be forced to take a cloud computing approach if we can't get around this. Next steps. Currently, I am planning on continuing to work on this project in the fall. So I plan on introducing more data to the model to improve its accuracy, exploring feature selection to reduce the feature generation required. And I'm also meeting with the Police Conservation District in August to discuss future collaborations. As for the app, I want to talk to someone with more development experience to see what kind of options I have. Lastly, I just want to give a big thank you to my mentors, Kirti and Amin, the lab group that I worked in at Wazoo, Agate for making this all possible, and Joaquin, who was the USDA advisor. Thank you all.